Welcome to another lesson. This one, surprisingly simple idea, surprisingly important results. Maximums and minimums, also called maxima and minima, depending on how you like to make plurals. So up to you if you want to say maximums and minimums or maxima and minima. This is super important because it turns out often the reason why someone would want to do math or hire a mathematician is to find the best way to do something. That might be the most profit, the least time, the least amount of energy, the highest amount of a chemical concentration, and that is nothing more than finding a maximum or a minimum. And it turns out we can use calculus, and just about everyone does use calculus to solve problems like this. Some simple, some surprisingly hard. So a couple of definitions, more than a couple, and a couple of big theorems in this section that if you understand them, you'll actually understand the methods as well. So let's go ahead and start off with our first big definition. F, which is some function, has an absolute max. This is also called a global max at c. So c is some x value. If f of c is bigger or equal to f of x for all x in its domain. Okay, so what this is just saying is that my y value is bigger than or equal to every other y value. And we do allow ties in this case. So I could write out the exact same thing for mins or minimums, but it's going to be the exact same except that instead of a greater than, it'll be a less than for the minimum. What is the smallest? These two things together, maxes and mins, are called the extreme values. So if anyone ever says find all extreme values, they mean find all the maxes and mins. And we're going to say absolute if we're talking about over the entire domain. Okay. So let's just take a little look here and see if on this simple graph we can identify the absolute maxes and mins. Take a second. Can you do it? I can do it. I've practiced. Here we go. The absolute max, right there. We should be careful. So this is the max. Sometimes people say the max value. And right here, the x value is called, we say this is the maximum is at c. That's the location of it. Sometimes people will say that c is the maximizer. Okay, I'm trying to limit the amount of notation I throw out there, but it's important to hear these words once or twice. So c would be the maximizer, so the thing that gives you the maximum. Great. So that's our absolute max or our global max. Where's the absolute minimum? Well, it looks like it is this endpoint right here. And for an absolute or global max, endpoints are just fine. We really want to talk about our entire domain, which does mean, by the way, that it is possible to not have an absolute max. What on earth might it look like if I said there was no absolute max? Could you graph it or come up with an example? Well, here's one case. Do you know what function that is? Well, the function I meant it to be, whether or not I drew it quite right, would be y equals 1 over x. Okay, and there is no point that is a maximum. If there is no point that is a maximum, then this thing is going to have no absolute max. I can make this even weirder. I could say, what if my function looked like this? This also has no absolute max or min. If you look at a graph, you should be able to point to it. And I want to kind of point to right here, right? Except for that point is not in my domain. And neither is this one. I want to say, oh yeah, that's where it is, but there isn't any specific value I can plug in. I can get closer and closer and closer to it. I could take a limit to describe that behavior. I could say it's bounded by it, but both of these functions are examples of no absolute max and no absolute min. Okay, different ways to do that. So be aware that you don't necessarily need to have one. You might still have limiting behavior, but you don't need to have an absolute max or min. Okay, this brings us to our next point. What is going on? What is going on with like this little thing here and this little thing here? It's got some behavior like a max or min. It's just not the biggest or the smallest overall. And I would like to have a word for that. I'd like to say, all right, well, it's still kind of special to us. So our next definition is a local max, or also called a relative max, at C, if the function value at C is bigger or equal to f of x when x is near C. And this is the only difference between absolute and local, as we say, we only care about close to it. And if you want to get more precise, we mean in some open interval containing C. Okay, so open intervals, those are the ones that might look like this. A little side note here. So I'll even show you a little notation for x in, this is the fancy math symbol for in, kind of like a round E, a comma b, and notice I did open parentheses so that we don't include a or b, where C is also in here. Okay, so there should be some open interval, some magic area nearby in which it's the biggest or the smallest. Okay, so can you draw some open interval nearby that says, well, at least here I'm the biggest or the smallest. In my local neighborhood, I am the biggest or the smallest. And that's what it means to be a local max or a local min. So I've already kind of given you an answer here. Let's see if we can identify all of my local maxes on this graph for this function. I bet you can do it. Here are my local maxes. And my local min. Looks like I just have one. Okay, fun point for you is that this is not a local min. And neither is this. Those are both not local minimums, which is odd because we just said this thing is our global minimum. However, endpoints aren't going to count for local because they don't exist in an open neighborhood. To have this definition of near open, we need to have points on the left or the right to compare to. So a weird little quirk of our definitions is that an endpoint can be a global max, but it cannot be a local max. This is going to be important because endpoints don't have derivatives at them. And this is one of the reasons why we want this definition, is so that we could take a derivative to find our local maxes and mins. Okay, let's do a quick example. Give it a shot here. Let's find all local minima of this fun function, f of x equals cosine of x on a given domain, 2 pi to 3 pi. Okay, I'm going to go ahead and not use calculus on this just yet. I'm going to go ahead and just draw the darn thing. Give it a second, see if you can draw this too. I'm going to draw it on this domain, which is going to involve quite a few ups and downs. Boop. 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 All right, there's my sketch. The period of cosine is 2 pi, negative 2 pi. So this should be a 3 pi right here. Great. We want to label all of my local minima. So that is just going to be this one, and not the one on the end, right? Endpoints don't count. So I have local mins at I have a local min of -1 at negative pi, and I have a local min of -1 at pi. Okay, so 2 local minimums. Those are also both going to count as my global minima, but the big difference here is that these endpoints don't. Okay, so you can have as many local minima as you want. If I made this an infinite domain, then I would have infinitely many local minima. Okay, so how do we go about finding them? How do we find local maxes and mins if we don't just graph them and point to them. How could we do this analytically? Well, that's going to involve calculus. So Fermat, pretty important mathematician. Looks like Fermat, but it's Fermat's theorem. He has a number of theorems. And he says if f has a local max or min at c, and it has a derivative at c, then, well, think about it. What would the derivative have to be? That derivative had better be 0. Okay, so if you got a local max or min and you got a derivative, the derivative has to be 0. Why? Well, if f prime is greater than 0, then you're still increasing. And so you're definitely not at a local max or min. And if f prime is less than 0, then you're decreasing, you're going down, and so you're definitely not at a local max or min. The only options are that you're either at the top of a hill or the bottom of a valley, in which case you have a horizontal tangent line, and then you would necessarily have a local max or min there. So if there's a local max and there's a derivative, it has to satisfy this. By the way, notice what's happening in these two cases is that the derivative is positive, it's 0, and then it's negative. And that's what it should look like if I have a local maximum. And a derivative going from negative to 0 to positive is what it should look like if I have a local minimum. That's called the first derivative test. Right, just checking that first derivative. Getting a little bit more involved, our second derivatives tell us about the concavity. And so having a negative concavity curving downwards is going to tell us we're at a maximum, and curving upwards, that second derivative being positive, is going to tell us we're curving upwards, and that's going to tell us we're at a minimum. That'll be called the second derivative test. Not the focus of this section, but good knowledge of the future or reminders depending on the order that we're going through this. Okay, how do we use this to find a minimum or maximum? We need one more definition and one more theorem. If c is called a critical number of a function f, well, I'm looking for local maxes or mins, what could possibly happen? Fermat's theorem tells me that I should check where the derivative is 0. But there's one case where Fermat's theorem doesn't apply, and we should check that also. So we should also check where the derivative doesn't exist. And by the way, these should all be in the domain. So that's it, right? Either Fermat's theorem applies and the derivative has to be 0, or it doesn't apply, in which case the derivative doesn't exist. If we just check for both of those, then we can find all of our local maxes and mins. Okay, and this is exactly what the next theorem says. All local extrema, so those are my mins and maxes, occur at critical numbers. So let's actually do this using some calculus. This is what we've been leading up to. One of two main things we're leading up to. Let's find all the critical numbers of 3x to the fourth minus 16x cubed plus 18x squared. All right, well, it's Calc 1. I bet we're taking a derivative. Let's give this a try. F prime of x. We're doing this to apply this theorem. We want to see if we can find our critical numbers. So we take the derivative, we get 12x cubed minus 48x squared plus 18, plus 36x. Looks pretty good. Okay, so now we want to check for two things. Where does this exist? Well, this is a polynomial. This is defined everywhere. Okay, so we don't need to worry about it not existing. What we need to check is, to find our critical numbers, is where is it 0? So we're just going to set it equal to 0. And believe it or not, our calculus part's over. Now this is an algebra question. Can we find where this is 0? Well, whenever you want to find the roots of this function, we're going to factor it, right? Factoring is our friend. You pull everything to one side and you factor. We may have seen already that sometimes this doesn't quite work and you need to estimate it using something like Newton's method, but this one's pretty nice. I can definitely pull out an x, so let's do that. Oops. So right away I know that 0 is going to be a solution, but I bet we could keep working this factor a little more. I bet I could pull out a 12. In fact, let's pull it all the way out. 12 x squared minus 4x plus 3. All right, and now all you got to do is solve that quadratic for where is that equal to 0. And you could either factor this some more, or if you were stuck, you could use the quadratic formula. So let's see, do I know how to factor this? Well, if it's nice, then it's probably going to have a 3 and a 1 in it, so that it'll multiply to 3. And they need to add to -1. Sorry, add to -4. There you go. Double check. Yep, that multiplies out. Great. If you were stuck, the quadratic formula would get you out of this mess, and sometimes you have no other real way of doing it than the quadratic formula. Okay, so what does that tell you? It's the solutions to this new equation. So x equals 0, 1, or 3, right? Where each of those factors is 0. And those are my critical numbers, the x values. We haven't actually found if those are local maxes or mins yet. We've just found that they're critical numbers, so those are the only numbers we should bother checking to decide if they are a max or a min. If we graph it, you can see it pretty fast. At 0, you're at this local min. At 1, you're at this local max. And at 3, you're at this local min. Okay, so we could plug it in. Let's see if we could figure out how to determine that. There's a couple of ways we could do this. Okay, one way is we could just plug in. We could just plug in and see, all right, am I going down or am I going up at each of these points? So if we just plug in into my derivative, I could say f prime of 0. I could do f prime of 1. I could f prime of 3. Oops, sorry, I don't want to do primes. I want to start over here. I want to do the functions themselves. F of 0 equals f of 1 equals f of 3. With a little bit of analysis of that and the end behavior, you could probably figure this out. There is a little bit of a more robust way to do this, which maybe you've seen before, that I mentioned a minute ago. We could do a first or second derivative test. Let's go ahead and see what that looks like. Other than graphing, and by the way, just depending on the problem, maybe you have a graph around, maybe you don't. But let's go ahead and take a look at our derivatives. So if I wanted to plot my derivatives and just if they're positive or negative, well, I know that at 0, I get a 0. And I know that at 1, I get a 0. And I know that at 3, I get a 0. Okay. So if I go ahead and I plug in a number like a 4, if I plug in a 4 in here into my derivative function right there, do I get something positive or negative? And it turns out I get a pretty big number, and it's going to be positive. Okay. If I go ahead and I plug in say 2 into my derivative function again, I just need to ask, do I get something positive or negative out? And I get a negative. I hope you're playing along. Go ahead and plugging these numbers in to that derivative to make sure this is true. I could plug in a number like a 0.5 and see that I get a positive number out. And I could plug in a number like, I don't know, -1, and I would get a negative number out. Cool. So because my derivative is continuous, the only places it could jump from positive to negative is crossing through those zeros. So I can pick whatever numbers I want to plug in. And now what you're seeing is that you've got a function that looks, your derivative function is going negative, positive. So your overall function is going to go, well, down, up, down, up. And we see that on the right over here too. It's just a little bit more detailed. So if I'm going from down to up, then that tells us, hey, at x equals 0, we have a local, well, if I'm going from down to up, it's a local min. At x equals 1, I'm going from up to down, so that would be a local, do you know? Max. And at x equals 3, I'm going from down to up, so I'm in the bottom of a valley, and this would be a local min. Very cool. Okay, more practice and details on this, as well as finding global maxes in the next video.